how do we know the inverse square law truly holds over all length scales, from the largest scales in the cosmos to the smallest?
These are small, but the ones out there are far away.
We've talked in other videos, like this one, with Professor Mordecai Milgram about his theory, which is called MOND, Modified Newtonian Dynamics, which explains away the need for dark matter by instead invoking a new form of gravitational force that operates not on local scales but on cosmic scales between galaxies and the internal dynamics of galaxies to explain the peculiar rotation curves of galaxies, first observed by Vera Rubin. Vera Rubin was trained right here at UC San Diego by none other than my late great colleagues Margaret and Jeffrey Burbage. But this is about a short-range gravity experiment, not on galaxy scales like this, but on the laboratory scales. And results are described in this paper, which you can find yourself for free in the archive at the link that's shown in the screen now. So, why should we test gravity at short distance scales? It's kind of nicely summarized here. Gravity has not been tested well below the sub-millimeter scale, where you might be able to first sense the effects of quantum gravitational effects. Those are obviously much, much smaller than the millimeter scale, but they're not as small, relatively speaking, as, say, from the tabletop or laboratory scale on Earth to the entire cosmos that the modified Newtonian gravity proposals seek to define.
Life is like this.
I want to make that smaller.
GR and quantum mechanics are incommensurate, incompatible with each other, and so you'd like to study that close to the regime scale, which both effects are operative, namely on the smallest scales and on the gravitational force fields that we can test in the laboratory. And lastly, if we could unify the standard model of particle physics and general relativity, we could potentially have the so-called theory of everything. And that may come in our lifetimes, or it may not come at all. There's no guarantee that forces and fields have to be unified just because that approach has worked so successfully throughout the past 100 years in the golden age of physics that we've been enjoying for quite some time. So, what is the inverse square law? Well, that's merely the fact observed and encapsulated in Newton's famous equation that the gravitational force field between two gravitating massive objects depends on the product of their masses times a universal constant called capital G, Newton's constant, and the inverse of the square of the distance between them. There could be alterations of this inverse square law at small scales that has so far evaded our detection because it's so difficult to measure the effects of gravity when you're talking about things that are smaller than, say, the length scale of your fingernails. It's actually easier to detect gravitational forces between planets and, say, the moon and the Earth than it is between objects that are separated by micron distance scales. As paradoxical as that may sound, you'd think it would be easier to measure forces over short distance scales. And of course, these divergences of the force, if you go to zero separation, formally, Newton's law is predicting an infinite force between two massive objects. But what does that really mean? Can you really get two massive classical objects to be located an infinitesimal distance away? No, you can't, but the question is, as you approach infinitesimal distances from finite distances, can you get a deviation from 1 over r squared behavior? That's what this research that Alyssa and her advisor worked on at Humboldt State. So where are we currently? Well, there are a series of experiments that have been carried out. These are really classical physics experiments that are being done with modern technology at the University of Washington. They're so-called ETVASH experiments, and the joke is that their name of the experiment is ETWASH, where WASH is for Washington, and they're looking for this equation that would parameterize a new gravitational potential. Rather than diverging as 1 over r, the force goes as the gradient or the derivative with respect to r of the potential. So if the potential varies as 1 over r, that means the force will go as 1 over r squared. In this case, the potential doesn't go just as 1 over r, the first leading term in the equation for V as a function of r, potential energy as a function of r, does depend as inverse on the distance, but then there's a modification, a so-called Yukawa term, which traces its name to the famous Japanese physicist, Yukawa, who predicted the behavior of subatomic particles and the strong nuclear force, pions and so forth. That was governed by a Yukawa term that fell off as an exponential, not as an inverse power law. And so by modifying the coupling from just being 1 inside the square brackets to being 1 plus this exponentially decaying term, which is parameterized by 2 numbers, the length scale over which it decays, which is lambda, and some amplitude, which is an energy scale, which is alpha. You have this two-dimensional parameter space of alpha and lambda. So the amount of the deviation and potential, alpha, is plotted here on the right as a function of the inverse of the length scale over which the deviation from inverse square law take place. In the Humboldt State University experiment, HSU, they predict they could get down to even lower values than these world-beating experiment at University of Washington. And they're working with the same team members, as you'll see, and if you read the paper, we'll show the paper here. Those authors are collaborators at the University of Washington. So at Humboldt State University, the lab that Alyssa was working in with her advisor looked like this. So they have a gravitational research lab where they're doing what's called torsion pendulum. A torsion pendulum is a pendulum that doesn't tick back and forth by swinging like a grandfather clock, but instead twists back and forth like a plate on a string. The amount of twisting as you bring in a closer plate to the torsion pendulum's bob, again, it's not oscillating in a plane, it's oscillating about an axis back and forth. And they measure that deviation as they bring in another material, perhaps made of a different substance as the main pendulum is made up of. So they've got a torsion pendulum with equal masses, so they have two plates separated by some distance. And this makes what's called a composition dipole if they're different materials. You could do it with similar materials, or you could do it with different materials. And the actual foundation of this experiment goes back to Cavendish in the 1700s, making these measurements in torsion pendulums as well. It's a classic experiment we do in physics labs, but this is on steroids with the Humboldt State University's team and approach to it. So the attractor mass causes the deflecting mass to oscillate, and that creates a time-dependent torque on the pendulum. And then you measure the period of the pendulum, the size of its oscillation, as a function of the separation between the attractor mass and the pendulum mass itself. And this allows you to look for deviations in what's called the weak equivalence principle, or in the inverse square law. And again, this can be parameterized by these two parameters, alpha and lambda. So this is not an easy experiment to do. In fact, I tried a version of the Cavendish experiment 30 years ago as a freshman at Case Western Reserve University. Go Spartans. In that measurement, I got an answer that was some 10 orders of magnitude off from the acceptable value of capital G in Newton's constant. That's embarrassing. But lucky for me, the tenure committee at UC San Diego never knew about those freshman lab blunders that yours truly made. Gravity is incredibly weak. There are interactions, electrostatic interactions, magnetic interactions. The test masses have to be brought in from different distances and changed and measured over those distances. There can be variations in temperature, as there often are diurnally throughout the day. The building has its own environmental effects. It has vibrational effects. Students come into the laboratory environment. They go into classrooms. There's traffic on the streets. All these things can be sensed by this exquisitely sensitive machine built at Humboldt State University. They have to keep isolated as best as possible the experimental apparatus from the surrounding environment. But you can't launch it into space, at least on the budget of a California State University like UCSD or Humboldt State University. So they make use of incredible precision control over the environment, including vacuum, shielding magnetically, electrostatic grounding, and what's called an active leveling system. That is the key enabling device at some level. The tilts in the apparatus can affect the measurement at the micron level, and that's very important for ruling out so-called systematic errors. Errors in the system, not in the fundamental forces, and it can confuse you that you've measured a deviation from the inverse square law, when actually it was just a deviation of your apparatus's tilt. So they actually build in what's called temperature compensation, where they can stretch or shrink the length of a leg of their apparatus to compensate for thermal variations in the laboratory or in the apparatus itself. They can measure this as they have here, and they can see the tiny, this is millionths of a radian. Radian's about 57 degrees. So you're measuring 57 1/millionths of a degree tilts, and you're doing that with very high accuracy over many, many day-long experimental data acquisition periods. It's really quite impressive that they can do this. And they need to do this to make contributions that people will believe to our understanding of gravity at small scales. Here's a block diagram, a schematic diagram of how the compensation works, what's called a PID, or proportional integral derivative control system. This is what's called a servo system that uses corrections and measurements like a thermostat does. It measures the difference between what you set the temperature at and what the room is actually reading, then applies heat or cold to compensate. But you can overshoot very easily and get into an oscillation with a thermostat unless you damp that by constraining what's called the integral term and applying a dissipative term, a derivative term, to correct for the oscillation so that you get a nice stable solution that's controllable, that's predictable, and this is called tuning the PID circuit, which is something Alyssa spent a lot of her time doing. LabVIEW, which is a nice GUI, graphical user interface programming term, which is very common in instructional laboratories. So if you come here to UC San Diego or you go to Humboldt State University, you'll get great experience doing control over servo motors and heaters and resistors and thermometers and doing everything digitally, acquiring and sampling an analog signal, temperature, length, etc., and then converting that to a digital signal and then correcting and compensating, applying compensatory signals to make a very stable and active control system. And this type of technique is used in everything from these tabletop type gravity experiments all the way up to the LIGO experiment that we've talked about many times, including with the two of the three leaders, Nobel Prize winners, Barry Barish and with Ray Weiss on this very channel. So here's a recording measurement where Alyssa's showing her data from the laboratory, tuning to get not an overall small value of the tilt, although that would be nice, but to get smaller and smaller variations and oscillations in the amount of tilt over time. And you see the very first runs that's shown at the top with no components of proportional integral derivative included. And then the final term, which has the lowest variation, the lowest oscillatory behavior over 1.2 days worth of data, and that shows the best behavior. And you see little interruptions that look like hash in the data. Those could be from people coming in the building, going out of the building. There's some periodic things. It could be from everything from interference from Wi-Fi to other effects that can be filtered out. But the goal has been achieved with just two terms, this proportional term and the derivative term, damping out the oscillations, but also correcting so that when it's too big a tilt, you correct, you heat, or you control the length of the apparatus, keeping it stable and its overall magnitude as small as possible. So they're still working on this. They're still trying to improve the tilt over time. The smaller they can get it, the more accurate they can measure both alpha and lambda. So they want to have tighter and tighter feedback control, but you can't over control. You can risk sending the system into an oscillation that also is unstable and doesn't improve your measurement whatsoever. And they want to understand and characterize their instrument much better. And you can read more about the results and the cutting edge nature of the field in these papers. And there's a paper in progress that Alyssa herself has been working on, so stay tuned for that. Look at the work of Professor Doyle at Humboldt State. And stay tuned for great results from both the ETVAS team and the HSU team. And stay tuned for more work from Alyssa Johnson, a rising star who we're lucky enough to have here at the UC San Diego system, where she's studying gravity in the laboratory. If you think of the entire cosmos as our laboratory, she's working on Simon's Observatory, measurements of primordial gravitational wave radiation. So if you like this measurement, you'd like to learn more about experimental searches for gravity, click here for this video about LIGO. And I'll see you in the next video.